So we just came up with this mechanism that says like, okay, we can do these mini hard forks where the only thing that changes is the block count. And they're still hard forks in the sense that it has to happen on the same block, right? Any kind of consensus rule we change, all the nodes on the network have to agree. And this is the main thing Fusaka is bringing through PeerDAS. Cryptography performance is maybe one of the biggest bottlenecks on this industry, and it is improving quickly, especially for everything around ZK, but we already save a lot and are able to scale Ethereum that way. But one downside is that
Welcome to the Fusaka Files, a Fusaka Upgrade Special Series by ECH Institute in collaboration with the Enterprise Ethereum Alliance. I am Pooja Ranjan from ECH.
And I am Paul Brody, the chairman of the Enterprise Ethereum Alliance, and so I'm your co-host for these little podcasts. We believe the truth about these upgrades is out there.
Of course, it is. And we are going to unpack the enterprise impact of Ethereum's upcoming Fusaka upgrades. So today, we are looking at two pivotal proposals, EIP 7594 PeerDAS and EIP 7892 Blob Parameter Only Hardforks. Together, they change how data availability and block parameters work, which could dramatically improve scalability for enterprise application. To explain the technical and enterprise perspective, we are joined by Tim Beiko from Ethereum Foundation. Welcome, Tim.
Thank you for having me.
Tim, I would love for you to maybe start by briefly explaining what PeerDAS is and why it is important for the Fusaka upgrade. But before that, if you could just introduce yourself to the audience.
Of course. I'm Tim. I work at the Ethereum Foundation. The main thing that I do there is coordinate the work on Ethereum core protocol development. So the way Ethereum works is we have a specification for the protocol, and there's many different production implementations of it, a bit like web browsers where you have Chrome, you have Safari, you have Firefox. They all allow to serve web page and to browse the webs. But they each have their different features. So Ethereum is structured the same way. Contributors to these protocol client implementations get together to discuss and debate, potential changes to Ethereum. So what I do is I kind of sit at the middle of this. I help facilitate the kind of road mapping and discussion process to get to what do we actually want to ship on Ethereum, and then work with all of these teams to go from these like specification and early ideas to final EIPs that are deployed and live in production. And I've been doing that since 2021 at the EF.
And this is something I really wanted to sort of chime in on. I think most business users don't really understand that Ethereum goes through regular network upgrades. It's not something that's kind of somebody poured concrete over it and it's done. Every 3 to 6 months, I think, what's the current number now? Like 17 network upgrades, all without downtime?
Something like that, yeah. So they tend to happen maybe more in the 6 to 12 month cadence. We don't follow like a fixed release schedule as much as figuring out what's the right scope and then doing the sufficient amount of testing to get there. But yeah, it is kind of this very thorough and like heavily test-driven development that we do. And we make sure that not only the specs are correct and sound, but that every single client implementation is safe and ready for production. And before these network upgrades going live, we'll typically even have these large bug bounties. So for this one that we're going to talk about, there's a $2 million bounty once the code is frozen. So if anyone finds issues that are like critical to the network, then we'll happily pay out these bounties to make sure that they don't hit the network once it's live. So yeah, through that process of just having like a very redundant system, big focus on testing, we've never had downtime on Ethereum.
That is awesome. I know people already know you because you have been the one who have been facilitating the all core dev, where we are making decisions on accepting all these proposals. And in today's episode, we are also going to cover a special kind of proposal, which is going to bring a different kind of upgrade. So we will learn more about it, but maybe we can go ahead and get started with the first proposal, which is EIP 7594 PeerDAS. So Tim, could you briefly explain what PeerDAS is and why is it important for the Fusaka upgrade?
Sure. So I'll take a step back from PeerDAS to kind of explain in the broader context of Ethereum what it's helping with. So Ethereum does two things. It is a virtual machine that processes computation, and it's also an environment where you can store data. both the computation and the data for Ethereum ends up being stored or executed by every node on the network. So this is why it's extremely expensive to deploy something to Ethereum, is because every line of code that executes or every bit of data that's stored is stored across the entire blockchain, and every node has to replicate this computational work. One way we've come up with to scale Ethereum in the past 5 years or so is this idea of layer 2s. And layer 2s are very ingenious because on Ethereum, it's more expensive to do computation than to store data, which makes sense. Computers work this way. RAM is more expensive than storage. So what layer 2s do is they execute all the computation outside of Ethereum in a different computing environment. So when you hear of like a layer 2 sequencer, this is what it does. It's like the computer that processes all the computation for all these layer 2 transactions. And then it posts the compressed data to execute all those computations back to Ethereum on layer 1. So they kind of exploit this asymmetry where computation is very expensive on Ethereum layer 1, data is cheaper, so we're going to do the computation elsewhere, post the data back on Ethereum, and they tend to have these like dispute resolution mechanisms such that if you ever disagree with the outcome of the computation, you're able to go back to Ethereum layer 1 and say, hey, this is the data we all agreed to. This is how it should be computed. And then you can use Ethereum layer 1 as kind of this arbiter of what is the right state. And so when layer 2s talk about things like fraud proofs or fault proofs, this is what they mean. And this is why we call them optimistic rollups, is we optimistically assume everything that's been posted is correct, but then anyone is able to look at the blockchain on layer 1 and say, hey, something's off, I'm going to dispute this. And then this means we only pay the high cost of computation for these like dispute resolution computations rather than every single transactions by users. So this is great. We already save a lot and are able to scale Ethereum that way. But one downside is that the data is then stored on Ethereum forever. And in practice, people consider the data to be final and settled like in relatively short order, right? The way layer 2s generally work today is they have a 7-day withdrawal period. So this means when you move your assets from L2 back to L1, they wait 7 days. If no one has claimed an issue, they'll give you your money back on L1. And effectively, the L2s were paying to store this data on Ethereum L1 forever, even though they really only need it for 7 days. So a couple of years ago, we came up with this idea of blob data, which is data that's stored on Ethereum layer 1, but only for about 3-4 weeks. And because it's stored less long, we're able to just charge less for it than data that's stored forever. So this is how Ethereum works today. So you kind of went from the stage where all the nodes store the data forever, all the nodes store the data for, some fixed period of time. And with Fusaka, one thing that we're bringing is effectively data being sharded around the entire network. So if you assume Ethereum has like a fixed capacity in terms of, storage and bandwidth, there's only so many nodes, they only have, so much bandwidth they can process. The question becomes, do we want to make sure every node has a copy of every data, or are we okay with some just redundancy factor on the network? If we can know that the data is stored, in this amount of replicas, and we can get cryptographic proofs from the holders of this data that say like, hey, I'm not going to send you all the data, but I'm going to send you a proof that I've actually got like the samples you've requested, then we can scale the total throughput. And this is the main thing Fusaka is bringing through PeerDAS, is laying this infrastructure on Ethereum to go from every node having to store all of the data to nodes being assigned part of this blob data and then doing cryptographic verification throughout the network to ensure that the people who are assigned other parts of the data actually have this. And then obviously responding to checks from others and providing proofs that they hold the data. We can get into the numbers later, but like at a high level, just this new architecture effectively gives us the ability to raise the amount of data on Ethereum by about an order of magnitude before starting to raise the actual bandwidth requirements, just because of now not everyone is storing everything.
I have so many questions. That was a fantastic explanation. Thank you. One of the things I first wanted to ask was, there are two kinds of layer 2 networks, basically. There are ZK rollups and there are optimistic rollups. And does this change only affect optimistic rollups because it's just dealing with these fraud proofs that are specific to optimistic rollups? Or does it affect every type of rollup, every type of layer 2 network?
Any type of layer 2 network. So the way ZK rollups work is instead of effectively having this dispute gate on chain, they post cryptographic proofs of what happened off chain, and anyone is able to run a verifier and verify those proofs. So it actually happens on a much quicker time window than optimistic rollups. And there's also a lot of designs now that are exploring how you can merge both, like effectively use like a ZK verifier for these optimistic rollup bridges. So not to get too into the weeds about rollups, but broadly here, like you can assume this applies to every type of rollup. And also like any just user of Ethereum, even if they were using L1 directly, and they just want to post data, have a proof that it was on Ethereum, and potentially be able to cryptographically attest to this in the future. You know, they don't have to be a rollup to do this. Like an application on L1 can just post data to the blobs. And if this data doesn't need to be stored on chain forever, they can always store it elsewhere and eventually just do a cryptographic proof that like, oh, last year on this block, we posted this data, and here's a proof that kind of ties it back to the current history.
Okay, now let's say I'm an enterprise, right? So I am, and there are a lot of different enterprise use cases, but one of the major ones that people are spending time and energy on is this question of like payments and transfers, especially things like stablecoin payments. It seems like on layer 2 networks, the price for transactions is already ridiculously low. But I read in some of the descriptions of the PeerDAS fork or the proposal that this will drive transaction costs down even lower. And I'm just wondering if you give me some sense of like for a layer 2 transaction, what kind of pricing impact do you foresee?
Yeah, that's a great question. And the transaction costs for L2s are already sub-cent in a lot of cases, right? I think of this less as like lowering the cost at this point as meeting demand, right? A lot of the L2s or potential L2s or enterprise we speak with, some of them aren't even using Ethereum yet because they know that like if they were to come, they would just saturate the entire demand, right? Like today, Ethereum blocks can have, you know, up to 6 blobs per block, which is not a lot, right? Even if that's like thousands of transactions compressed, most enterprises alone could do more than that. So I think, yeah, this price is already very, very low. And it's more a question of can we offer more supply so that we can reach like much like more use cases and yeah, different like markets that we're just not addressing today because we don't have the capacity.
So this is actually something that we've spent some time at EY thinking about. So I have one client in the medical space, and they anticipate that to bring a single product line on chain, they would need capacity for about 4 million transactions a day just from that one product line, because each one, they make about 500,000 serialized packages of medicine. And if it's a serial number, it's an NFT, not a fungible token. Yeah. And on average, each packet of medicine moves 4 times before it reaches the end patient. So 500,000 times 4, that's an average of 2 million transactions a day for NFTs. So that's for one product line. So I think your point is a fair one. Tell me, is there a trade-off? Like, so I'm getting a cheaper transaction, but is it going to take longer? I mean, now you're splitting up all the data. So if I need to search the data, is it going to take me longer to find it and verify the truthfulness of a transaction?
No. So the idea is still that like, and the way Ethereum works already is we have blocks every 12 seconds. For every one of those blocks, we sample in the validator set who are the validators that are going to attest and obviously who's the validator that's going to propose this block and whatnot. So sampling works the same for data as well. So we expect that the sum of the data is stored across the sum of the validator set, but that when we sample, we're able to get at least one kind of party who can prove the data. So there's no extra delays or anything like that. And then I think in terms of like the enterprise use cases you described, the way to think about the trade-off is more who needs to be able to prove what, where you can think of when you post something on Ethereum layer 1, you're saying the entire world now can attest to this. And you kind of get the highest level of like openness and kind of trust in these statements, but this is probably not true of everything. Like for example, if you're aggregating, you know, millions of serial numbers, you could imagine maybe something like there is some set of entities that verify the integrity, and you know they can kind of bundle this and say like, okay, I looked at this batch and like I can ensure that like this entire batch is correct, and then that entity can post like an aggregated commitment to say Ethereum layer 1 or an Ethereum layer 2, and you know if someone then has like a challenge or an issue, they can say like, okay, there's like 5 entities verifying this or 5 people verifying this, 4 out of the 5 agree, this one disagrees. And then you kind of have to trust that there's something off chain, some way to resolve this. And I think a lot of these enterprise use cases have this, right? Like they're not things that fully exist on chain. If you're talking about a physical product or anything in the real world, hopefully there are some mechanisms you have around quality control and whatnot, but you can still get a massive increase in terms of transparency, in terms of efficiency, if you're not putting all of the raw data on chain, because you can at least pinpoint like, okay, which parts of the process are critical, who is accountable for them, and if something fails, then, you know, have a way to diagnose this.
That's really amazing. Thank you. Now, I've got one other sort of question, which is a lot of our conversation has been focused on like the cost of storing data versus computation. Some transactions are data intensive, but other transactions are compute intensive, right? So if I have a very complex like DeFi ecosystem with collateralized lending or some other kind of tool, it's going to use a lot of gas. I know from an EY perspective, we care a lot about privacy. And when we run our zero knowledge circuits, the gas fees are much, much higher. So is this going to lower gas fees even for computationally expensive things or only for storage expensive things?
It'll create more bandwidth for L2s generally. So if you're doing expensive computation on L2, it will help. It will help less than if you're doing data intensive things. And cryptography, like, I mean, you know this, but like, yes, cryptography performance is maybe one of the biggest bottlenecks on this industry. And it is improving quickly, especially for everything around ZK. But yeah, fundamentally, this is like the one thing we're bottleneck, the speed at which we can do ZK-proof verification. That said, for non-ZK computation, I think a big area of research now where it does feel like a lot of Ethereum, call it like vanilla computation, is probably slightly overpriced. And we are looking at how to effectively either increase the cost of storage to offset it, but to better subsidize just like vanilla computation on Ethereum. It's not coming in this upgrade, but it's something you should expect to see in the coming upgrade after Fusaka.
In our own estimates, in our work on ZK computation, we think we're about 1,000 times more functional or faster and efficient than we were when we started 7 or 8 years ago. So that's a really good result. But we were starting from an insanely high expensive transaction fee. Now we've achieved a reasonable one, but I think if we feel like we need to get another order of magnitude lower to really onboard large numbers of business users in like big supply chain use cases for transactions under privacy, which are so compute intensive.
Yeah. I was just going to say on the ZK point, like this is something that shows up in different parts of the protocol. Like, again, as you know, we're looking at the ZK for proof of Ethereum execution, for consensus. And it is true, like, yeah, 4 or 5 years ago, all the numbers you saw were like, oh, we're like 1,000x or 10,000x away from this being viable. And it was easy to almost dismiss this. But now, like, yes, we are in a lot of use cases within an order of magnitude. And it's really been like this exponential curve kind of coming down. And it feels like we're just at the frontier of things being like economically and computationally possible. So I expect in 2 or 3 years, this will be pretty much the default, right? Like we'll get to a spot where the performance is good. Then after that, obviously people will want to test it and ensure it's reliable and bug free. But it really does feel like we're kind of on the cusp of things going from like ZK being practical to ZK becoming the default.
That's pretty awesome. So blob data were introduced by EIP 4844 in earlier upgrade, and now we are adding infrastructure to verify and make these data available for layer 2, expecting that it's going to help get the price lower and we could have more transactions on chain. Today, we are also discussing another proposal which is related to Blob. So I would love to hear your take on Blob Parameters Only Hardforks that is being proposed with this Fusaka upgrade. How does this mechanism help adjust Ethereum capacity without the full upgrade? And why do you think it is important to have BPOs independent of Ethereum upgrade?
Yeah. So the idea for this, like I mentioned earlier, we're moving to an entire new mechanism of how we kind of handle blob data on Ethereum. And this mechanism allows us to scale, but before we scale, we want to be pretty confident that it works. So what we're doing with the original activation of this upgrade is just saying, okay, we're going to keep the amount of data constant, but we're just going to change like the backend and make sure this works. And we're obviously quite confident at this point that it works. Just to kind of isolate variables and ensure we have a high security threshold, we've decided to stagger the actual capacity upgrades for blobs over time. And so this is what these blob parameter only forks are, is they're effectively saying, okay, the new system is in place. Now let's just like tune this number up. And on Ethereum's execution layer for gas limit, the validators control this. We don't need hard forks. The validators can just vote on the gas limit and it moves up and down alone. Whereas for blobs, because it's also like a smaller discrete number, right? Like we have 6 per blobs now, and eventually we're going to go to 9 and then to 10 and 14 and whatnot. It's less of a like continuous value to tweak. So we just came up with this mechanism that says like, okay, we can do these mini hard forks where the only thing that changes is the blob count. And they're still hard forks in the sense that it has to happen on the same block, right? Any kind of consensus rule we change, all the nodes on the network have to agree. But because we already kind of know what is going to happen, we wanted to make sure to decouple these from like the features that go into hard forks. And like we were just talking at the start of this episode, it usually takes us 6 to 12 months to ship a hard fork. There's a lot of debate and conversation and testing that goes into it. So we want to make sure that we have a way to just continuously increase the amount of blobs we have on Ethereum without having to go through this entire governance process. So this is the rationale for these blob parameter forks. So with the original release for Fusaka, we're going to have the activation of PeerDAS and then the first 2 blob parameter forks going live in the weeks after. And then we expect in Q1 of next year, we'll put together another set of upgrades for a couple more blob parameter forks. And then lastly, the thing that this allows us to do is in the world where we saw an issue, right? Like between, say, blob parameter fork 1 and 2, there's something, we can always cancel the next one, right? We can just put out another client release that says, okay, actually don't fork in a couple weeks and allow us to deal with this. So it's just effectively a nice way to get this capacity on chain in a more steady rollout rather than a step function change.
So one of the things that I've been wondering about is I've been hearing a lot about how some people are saying blobs are mispriced or they're too cheap and that the L2s are kind of taking value from Ethereum. And so one of the things I was wondering is does these upgrades affect blob pricing, and what is kind of some of the current thinking about that? Because that's obviously enormously important to the business models of layer 2 networks and to the business models of companies that are thinking about implementing layer 2 networks.
Yes, so there is another EIP in Fusaka focused on blob pricing updates that mostly aims to make it more predictable. And so this is EIP 7918. It might actually be worth diving into the details, but I can give you the high level overview. The way that the blob pricing was set is effectively based on rolling averages. And we set it very low, expecting that it would be like a one-time ramp up, past the floor, and then it would kind of settle there. But one thing that we've seen is that there are actually periods where there's just right now very little blobs on Ethereum, and it's been the price kind of go back to this floor again. And what this creates is not necessarily that the pricing is too cheap, but it's too volatile, meaning that we'll have these cases where for a couple hours, there hasn't been blobs, and all of a sudden, there's an NFT drop on Arbitrum, and then there's a ton of traffic, and the price goes up exponentially in a very short amount of time, making it hard for people to get reliability. And Arbitrum even had a system for this because this happened on their network. I think when they launched their token, the price just shot up so much that it became cheaper for them to store data on the permanent data stored in the blobs because of this mispricing. So EIP 7918 is just going to help with this to make sure that there's a kind of more smooth, changes in pricing and help make things generally more predictable. Yeah, so I think that would be an interesting one to bring the authors on and kind of get into the weeds of exactly how the entire mechanism works.
Okay, so but otherwise, this second EIP 7892 is really just about a smooth implementation of 7594 so that there's no big radical change. And if there is any problems, they get caught. And this is just more about Ethereum being pretty cautious generally about not being reckless with upgrades. It's not a move fast and break things kind of mentality.
Yeah, correct. So we want to make sure we can actually commit to scaling, right? We don't want to say okay, we have this new system and now we're not using it for a year because we're debating this other random feature. So the idea is to decouple the actual scaling of the blobs from the rest of the governance process, and then also to just roll it out in a more measured way.
Well, I have a question with respect to preparation. How do you think that enterprise people should prepare for these 2 EIPs getting included in Fusaka upgrade? Do you have any special guidelines that they should be mindful of, or any hardware requirement? I understand there is an informational EIP that provides information on hardware that should be there in order to run nodes, but anything specific that people should be mindful of?
Yeah, if you're a staker and whatnot, then yes, you should review those hardware requirements. I assume we can link the EIP and the details in the show notes. But if you're an enterprise that just wants to use the chain, I think, yes, reconsidering some use cases that you thought might have been previously impossible because of data constraints on Ethereum is something that would be wise to do. And I would look at obviously these 2 EIPs and the current numbers, but I think what's nice is they also allow you to kind of start forecasting the blob capacity continuing to increase beyond this initial fork. And I think this is really where the interesting thing is, where there's just, like we were discussing, there are some use cases where just the sheer scale was not possible before. It was almost independent of the price, whereas now, like, okay, there might be things that are like cost effective to do that leverages data. So yeah.
Tim, thank you so much. This has been incredibly interesting. I look forward to seeing you in person at DevConnect in Argentina.
Thank you so much for having me. This has been great.
Well, thank you, listeners. Check out our show notes for related resources and links. And please follow ECH Institute on YouTube and Spotify for more on Fusaka Files. Until next time, keep building on Ethereum.